Okay, in this video, which is going to cover the main ideas from Chapter 13 that you're required to know, we're going to talk about universal gravitation. So far in this class, we've talked a lot about gravity, but we've really only talked about it near the surface of the Earth, right? So we know that near the surface of the Earth, that we have that the magnitude of the force due to gravity is simply equal to the weight, which is the mass times our g, which near the surface of the Earth is around 9.8 meters per second squared. But we can now write a general equation where you're not necessarily right near the surface of the Earth. And we can see that the magnitude of the force of gravity that acts between two masses is equal to a gravitational constant g times the first mass multiplied by the second mass divided by the distance between them squared. So we had seen this briefly previously in the course, and now we're revisiting this idea. G is, like I said, a gravitational constant. It's equal to 6.673 times 10 to the minus 11th, and the units on that are Newton meters squared per kilogram squared. Now, of course, the gravitational force is an attractive force, right? You drop a ball, it falls to the ground. So this is now an attractive force for the direction of this force of gravity. It's going to be an attractive force between M1 and M2. So if you have, say, M1 here, and then M2 over here, and it doesn't matter what their sizes are, then you would have the force that each one exerts on the other pointing directly towards the center of that object, basically the center of mass of those objects. Now we have to remember from Newton's third law that these are going to be equal magnitudes of forces. So that the force that M1 exerts on M2 is equal and opposite to the force that M2 exerts on M1. Does not matter the difference in the masses. Same magnitude. So the Earth pulls on the Moon just as much as the Moon pulls on the Earth. This pen pulls on the Earth as much as the Earth pulls on the pen. So we have those same magnitudes of forces. The direction, again, points from one towards the center of the other. Okay, so now we can introduce the idea of a gravitational field, which is a useful concept to talk about because when you get to next semester, you'll talk about the electric field and the magnetic field, and having some more concrete thing to visualize in terms of these fields is helpful. So the gravitational field will actually be the vector g, and it's going to be defined as the gravitational force that a mass would experience if it was placed in that field. So you can imagine that everywhere around the Earth there's a gravitational field pointing towards the center of the Earth, and that if I place a mass in that field, then I know the force that it would experience. It's simply equal to m times g. So this mass here is a so-called test mass that can be placed in this field and then determine the force. So even though a force doesn't exist everywhere, because you need a mass in order to have a force, a gravitational field, the idea of a gravitational field, can exist everywhere in space. So you have a gravitational field that exists everywhere around the Earth, and it tells you what force a given mass would experience. Okay, so if we now look at our universal gravitational equation, where we have that the force is equal to, now I'll call it little m, our test mass, times some big M over r squared. Then this mass here, little m, is the test mass, and big M is the mass that's creating the gravitational field. Then what we can see is that our gravitational field is equal to negative g and then it's going to be equal to this force divided by the test mass, so that mass just cancels. So times capital M over r squared, and then it'll be in what we call the r hat direction, which means that it points in towards the center of M. So negative r hat means that it points towards the center of mass M. So that denotes the direction. And so what we can do then is draw this gravitational field for some mass M. Say the Earth or the Sun has a gravitational field around it, even this pen. Then it would be equal to this gravitational constant times the mass of the object. So the bigger the mass, the bigger the gravitational field. And then it's going to drop off with distance. So the farther you go away, r, from the center of the mass, then the smaller the field will be. So say near the surface of the Earth, our gravitational field might look something like this, where at any given location, right, I'm only drawing a couple of the arrows, there's sort of a continuous amount of arrows here. These are just used to denote the strength at a given radius. But then as you go further out, the arrows get smaller. So you might denote then the gravitational field in this way, where you have, as r increases here, then the gravitational field gets smaller. And these lines denote the gravitational field at each point, which denote the force, the gravitational force at each location. So if we look at the specific example of Earth, then if we write the gravitational field of Earth and we find the magnitude of it, it's going to be equal to the gravitational constant times the mass of the Earth, right? That's the mass of the object. And then at the surface of the Earth, then it would be equal, from the center of mass to the location, would simply be equal to the radius of the Earth squared. So this is the Earth at the surface. And if you plug in these numbers, 6.67 times 10 to the minus the 11th, the mass of the Earth, the radius of the Earth squared, it turns out that this value for the magnitude of the gravitational field is 9.8 meters per second squared, which should look very familiar. So this value of our acceleration due to gravity for an object in free fall is exactly equal to and comes directly from this universal gravitation and finding the magnitude of the gravitational field at the surface of the Earth. Alright, just like we had to revisit the idea of the gravitational force for universal gravitation, we want to now revisit the idea of gravitational potential energy. So recall that at the surface of the Earth, that the gravitational potential energy, or the change in the gravitational potential energy, because that's again what's the relevant quantity, is equal to mg times the change in height. Now, in general, if we're now going to talk about our general expression for the gravitational potential energy, we can go back to this definition of potential energy, which is that it's equal to the negative integral from some position Ri to some position R final of the force that acts dr. So this came from the idea that the force was equal to du dx, right? So f sub x equals du dx. This is now the integral form of that same equation. So for us, the force is equal to g times m1, m2 over r squared. And as with all gravitational potential energy, you need to pick somewhere to be u equals 0, right? It was arbitrary where you picked y equals 0, so it's arbitrary where you pick u equal to be 0. So for the convention for here is that we say that ug equals 0 at r equals infinity, so that when you're infinitely far away from an object, you have no gravitational potential energy. And so what that means is that the gravitational potential energy is 0 when Fg equals 0. So what that means then, though, is that as you get closer and closer to an object, right, usually your gravitational potential energy gets smaller and smaller and smaller and smaller, right? You make something high up, and then the gravitational potential energy gets bigger and bigger and bigger. So if the biggest it ever is 0, then all the other values are going to be negative. So UG as a function of R for R less than infinity will be negative. And it'll get more and more negative as you get closer and closer to the object. So we can then go ahead and write what the gravitational potential energy as a function of R will be, and it's simply then the integral of this dr. So 1 over r squared dr gives us negative g times m1 m2 over r. And then this again is relative to UG equaling 0 at r equal infinity. And that is now our expression for the gravitational potential energy of some object the separation of two objects, say a ball and the earth, some separation r away, and then this will give you the gravitational potential energy relative to UG equals 0 at r equals infinity. And again, note that it's negative, but that is okay. A lot of times students panic because it's negative energy, but again, it's a negative gravitational potential energy, which is an arbitrary thing because it depends on the convention that you use. But this, again, is the common convention. All right, so that's the gravitational potential energy, which we can then express here. So when we start talking about conservation of energy, we're also going to want to be able to talk about the kinetic energy. So if we look at kinetic energy in circular orbits, to simplify everything a little bit, we can say that, let's say you have some mass m, and then there's a little mass, small m, that's some distance r away. And let's say that it's moving in a circle around this mass. So at some given instant, its velocity, v, is always perpendicular to r. So if we have a constant speed, and there's a mass m orbiting a larger mass, big M, and it's a distance r from the center, then now we actually just go back to using Newton's second law to talk about this, right? It's a mass that's moving at a constant speed around an object that's exerting a force on it. So the centripetal force, the force that's keeping it moving in this circle, is the gravitational force that's acting. So we remember that the sum of forces is equal to the mass times the acceleration. In this case, the acceleration is centripetal acceleration, mv squared over r. And so we can write then that the only force that's acting on m is the gravitational force. So that tells us that the gravitational force Fg is going to be equal to mv squared over r. So plugging in what we know for the gravitational force is g times capital M times little m over r squared, so that's F sub g, is equal to mv squared over r. And this is a little m because that's the mass of the object that's orbiting. So that's the one that uses here. So that's the one that cancels out. And we can now see that there's an equation for the speed of an object in circular orbit, which is equal to g times capital M over r. And that's the speed squared for a circular orbit. And now what's interesting is that this is independent of little m. So that anything that is orbiting the Earth, say for example, satellites, the Earth has a fixed mass, capital M, so the speed that they have for a circular orbit is entirely determined by the radius. So regardless of a light object or a heavy object, satellites, say, orbiting at some given radius, they will all have the same speed. Using this expression, then, we can write an equation for the kinetic energy, which is going to be equal to 1/2 mv squared. So that's then simply equal to m times v squared. So I'm going to write g times little m times big M over 2r. So now we have an expression for the kinetic energy of an object, mass m, in circular orbit around a larger mass, capital M, and separated by a distance r. So if this is independent of m, we can note that, again, that the speed is determined by the radius, but then that also lets us say that the radius is determined by the speed and by the mass of the planet. So you can say that, note that the radius is equal to g times m over v squared. So r is determined by the speed and by the mass of the planet or star, as the case may be. So we can now combine these ideas of gravitational potential energy and kinetic energy of circular orbits to talk about overall energy considerations in circular orbits. We have the kinetic energy, as we just found, was g times m over 2r, and the gravitational potential energy was negative g little m big M over r. Note these are very similar, although this one has a negative sign and there's no 2. But they are very similar, which actually allows you to combine them very nicely when you talk about the total energy, which is simply going to be equal to the kinetic energy plus the gravitational potential energy, which would be equal to E total. So that's g times little m big M over 2r, and then plus negative g times mm over r. And so if you combine these, right, you can see that this is 1/2 minus 1, basically. So you end up with negative 1/2. So you end up with negative g mm over 2r. And again, it's okay that it's negative because that just hinges on the idea of where we took our convention for the gravitational potential energy. And what's going to matter when you start going through this is not what's the absolute amount of energy, but what is the change in energy. All right, this is an example from chapter 13. And the question asked to find the minimum energy needed to launch a satellite that was initially at rest on the Earth's surface into orbit at some height h above the Earth's surface, and assume no loss to internal energy. So the idea here is, what is the energy that you need to add in order to move it from the surface into orbit? So really what you're doing is comparing the energy that it started with when it's at rest, not the Earth's surface, the energy it would have once it's in orbit, and finding what the difference is. So we're going to write down the initial and final energies, and then take the difference. And that's our goal for this problem. So, well, the initial kinetic energy is 0. It's not in a circular orbit, so we can't use that expression. The gravitational potential energy initially is negative g times the mass m. It didn't tell you the mass of the satellite, but remember that often that's going to drop out, times the mass of the Earth over the radius of the Earth. This is our gravitational potential energy equation, and I just plugged in for our values. The final kinetic energy plus the final gravitational potential energy is going to be equal to the total final energy for circular orbits that we just covered in the previous video. And that would then be equal to negative g times little m times the mass of the Earth over 2 times little r, which is the separation between the satellite and the object it's orbiting. So you can't just put an h here, and that's the most common mistake, because the separation is not h. The separation is h plus the radius of the Earth, right? It went from being at the radius of the Earth away to being h plus the radius of the Earth away. So we have now two expressions for the energy and we want to find the difference between them. So basically, we can then say that what we want is equal to K final plus UG final, which is equal to E total final. And then we want E total final minus the E total initial. And so we can then say that this is going to be equal to negative G times the mass of the Earth times little m times 2 plus H plus RE, so I'm just writing down the final total energy, and then minus the initial total energy. And when you work with these problems, you're going to have to be very careful of your negative signs, because there's a lot of them floating around, and a lot of times you have a minus, a negative. So just be extremely careful. So minus your initial energy. And then when you do that, you can see here that a lot of these terms are similar. You have GMME and GMME here. And so I'm going to just pull those out. I'm going to write G times M times ME. This term is positive, so I'm going to put it first. It's going to be 1 over RE, and then minus 1 over 2 times RE plus H. And then that's as simplified as it needs to be, unless you were given H in terms of RE, in which case you could simplify it more.